Hi everyone, welcome back to the A to Z of Python. Today is day 2, which means the letter is B, and to me that means Bitwise Operators. So that's what we'll be talking about today. If you're not familiar with binary, this isn't going to make any sense to you, and I don't want to spend too much time talking about counting in binary because it is kind of a fundamental concept, and you can go watch a video or something or read a quick article and figure it out. I will spend about 10 seconds. I'll do one quick example and then we'll move on. I've created this handy sort of cheat sheet here that's going to print out what each function does, and you can get this code. I'll put a link in the description. As this series goes on, you can download all the code that I've done and mess with it and see how it works. So binary basically is the way the computer counts. And the way it works is it starts at 0 and it goes up to very, very high numbers, but it does it by, think of it as you're not counting from 1 to 10, you're counting kind of in these 1, 2, 4, 8, 16, and as it turns out, with these combination of numbers you can actually create any number that you want. And the way that the computer decides which numbers to add is it will take something like this, which is a series of bits together here, and it will count using this number grid from the right to the left. And if there's a 0, it just counts 0. If there's a 1, it counts the actual number itself, and you add those up and you get the number. So let's take a look at this one. So we have a 0 here, so we'll have a 0 for 1. We have a 1 here, so we'll have 2. So we have 0, 2. There's a 1 in the next place, so there would be 4. So we'll add a 4. There's a 0 in the next place, which is 8. So we'll put a 0 for 8. And they have 16 and 32. The next two also have a 1. So if we basically go over from right to left, and wherever you see a 0, you just ignore it. And wherever you see a 1, you add that number. We can construct this here and realize that this number is 54. If it's 0, it's just a 0. Okay, so that's how that works. And if we run this code, what we can see is if we convert 54 into binary using this little string format here, this is actually the number that we get. And if we turn around and we convert that same binary string into an integer, we will get 54. So this proves to you that the math that we just looked at is actually correct. And that's how binary works. It's basically how the computer counts up. And it's pretty straightforward. So first thing I want to look at is I'm going to assign two variables here. One x, which is going to be equal to 27, and one is y, it's equal to 12. We're going to use these same variables throughout all the different bitwise operator examples that we're going to do. So the first one that we want to look at is this guy right here, and if you've seen that before, you'll know it's called a left shift, and you can see these left two pointing arrows here that indicate that's a left shift. What that's going to do is we're going to take number 27 represented in binary, okay, so 27 represented in binary, and we're going to shift that to the left 2 places, and the result is the same number with 2 zeros attached to the right side. So it just kind of bumps these over 2 spots and puts a 0 in. And what happens is you actually end up with a larger number when you do it that way. And it's, just adds, pretty much 2 of the whatever the largest numbers are onto it. So in this case, 27 left shift 2 is 108. And you could left shift by as many numbers as you want, and it'll essentially push, if we look at our binary chart, it pushes all the bits over. It kind of adds on some bigger bits, okay, and these will be zeros filled in this case 2. So 2 zeros inserted here, and all those other ones get shifted over, which adds some bigger numbers on. So a 27 or any number, any variable left shifted will end up with a larger number and can be some cases quite a bit larger depending on how far you shift it. So logically the next one is the opposite of that, which is the right shift. And the bitwise operator right shift is just like you would think. Okay, instead of the left shift with the left little arrows there, we have the two right arrows. And this does essentially the opposite of the other one, and it takes a representation, a binary representation of a number, and pushes it to the right and drops off the numbers there. And so we've done it two places. So we're essentially going to get rid of the two rightmost numbers, and we're left with this here, which in binary, this is a 6. Okay, so this will result in a smaller number, pretty much no matter how you do it. Alright, so those are, I would say, two of the most straightforward ones. You're literally just adding zeros to the right or dropping numbers off of the right, depending on which way you kind of push or pull your binary. The next one is this little ampersand here. This is known as a bitwise AND, aptly named. And what we'll do here is we'll use both x and y variables here. And we'll do 27 bitwise AND 12. And what does it do? Well, it compares each bit, and if both of the bits are 1, it will output a 1. And otherwise, it'll output a 0. So let's say, you got to look, these arrows are showing you that you're going to calculate by going down each column. So what we're looking for is a match of 1s. So we have a 1 and a 0, so there's no match. So the resulting bit is 0. We have a 1 and a 0, so no match. So the resulting bit is 0. We have a 0 and a 1, still not a match, okay, because they need to both be 1. So if there's a 0 in either of those, it's going to be 0 down here. Finally, we have a 1 and a 1, so that equals 1. And that's how that works. So this is the number that we get to. And this would technically, if we represented this empty space here, this is technically a 0 as a placeholder, which would leave us with a 0 here as a placeholder. And so the way this is printed out, it's dropping that extra 0. And so you can imagine this with an extra 0 if it helps. So 1, 0, 0. That's the same number whether the 0 is there or not. In this case, it's 8. So it can result in an equal number, but it generally will result in a smaller number. So this would shrink the integer that you're working with. Alright, so moving right along, nice and quick here. This is what's called a bitwise OR. Alright, so what that means is if both of them are 0, the output is 0, otherwise you output a 1. So if you notice here, we'll compare downward again for each column of numbers here. We have a 1 and a 0, so they're not both 0, so we'll put a 1. A 1 and a 0, so they're not both 0, so we'll put a 1. 0, 1, they're not both 0, so we'll put a 1. So forth. So 1 and 1, that's another one. They're not both 0, so we'll put a 1. And then this is a 1 and kind of like a hidden 0 there. And so we'll end up with a 1. So in this case, the numbers 27 and 12, when you use the bitwise OR operation on there, you're actually not going to get any zeros at all, because in no particular bit comparison did both bits equal 0. Alright, so we'll move on. This one is called the bitwise complement. This is the one that when you watch a tutorial on how this works, everyone glosses over this, and for good reason. It's actually kind of complicated to explain, especially in a brief video like this one. And it has to do with the way the operation works and the way the information is displayed when you print it out. There's some things that go on sort of behind the scenes that aren't really that intuitive, and it's kind of confusing. So if we run this and we say we take 27, so our x variable there, and we get the complement of that, we end up with 28. So we can look in our code here, and where are we at here? It says it returns the complement of x. So what that means is the complement of x happens to be negative x minus 1. That's just how that works. Or you could think of it as a negative x minus 1, or excuse me, negative x plus 1. Same thing. Okay, so this is the way from, Python. If you look in the documentation, I believe this is exactly where this came from. It tells you it's equal to negative x minus 1. So if you don't care how it works, and you don't need to know how it works, just know that if you run this operation, you will get the negative number, but one less than the original. So if you put in a 12, you would get negative 13. If you put in a 5, you would get negative 6. In this case, we put in 27. The result is a negative 28. What this does, and you'll not see this illustrated here, but I'll just kind of go over it. And if you're interested in seeing how that's visually represented, I'll pop another screen up here to kind of show you how that works. But this is binary for 27. And if we print out the bitwise complement, which we've done here. Okay, so this little print command here is actually how we're getting this. This is negative 28, so this is 28 in binary and it's negative. Now that's not how negative 28 actually looks as far as the computer is concerned when it's storing the value, but when you print it out, for ease of reading this, we can just treat it almost like a positive binary number, and then we know it's negative because we have this negative here in the front. This is not how this number is really stored in memory, so that's what confuses the hell out of people. So what it's doing, if you really want to know, let's see if I can find the explanation. I've got it here somewhere. I'll never find it now that I need it. But let's see. How would I find? I don't know. Okay, anyway, that's not important. I don't want to get too deep into it. What happens is this operation takes the bits of any particular number and it flips them, meaning the ones would become zeros and the zeros would become ones. So you could imagine this number as 00100 after you run this operation. And interestingly enough, in binary, that number happens to add up to negative 28. And you can figure that out because if you take 28 and you flip the bits on 28 and you add 1, which is what it's actually doing in the background, and why it does that, why does it add 1? Well, it has to do with handling zeros and negative zeros and things like that. Well, long story short, that's what it's doing. It's taking that number, flipping it and adding 1. So if we were to take 28, flip the bits, add 1, we would get the same exact bit string as if we just inverted 27. And so in theory, those numbers are the same number. And so when you just flip the bits of an integer, like say 27, the computer will interpret the results as negative 28. And that's what that's doing. And I think von Neumann figured that out way back in the day when they were trying to figure out how to represent negative numbers in the computer language. And it's called 2's complement. Okay, that's how negative numbers are stored. Most programming languages operate that way, basically all of them. And if you want to know more, just look up 2's complement. And there's a great Wikipedia article and there's a great Stack Overflow explanation of how that works. And you can learn more about how that works. But if you don't care, again, if you do this, you'll get negative 28. That's just how that works. The last one, but certainly not least, is what's called Bitwise XOR. And this one's kind of neat. This one, I think, to me, has the most functional application. And this one I'm going to actually show you an example of how this might be used in the real world. But what it does is it compares each bit, and so the output bit here, I should have a little dash line there, sorry, I'll add that in later, but the output bit here, alright, it equals the X bit if the Y bit is 0. So what we're doing is this is kind of a template, if you could think of it that way. So wherever there's a 0 here, we just copy the value down. And wherever there's a 1, we copy the opposite value. So we have the Y bit is 0. So we'll just take whatever this bit is, which is 1, and move it down. Y bit 0, so we'll take this bit and move it down. Y bit 1, so we'll take this bit and we'll copy the opposite of it, the complement, and so on and so forth. And what we end up with is this number here. And so if you look at it from a numerical standpoint, which you probably won't, but if you did, this operation would actually, the XOR operation would be 27 XOR 12 would equal 23. So you're probably thinking, well, what the hell does that matter? I mean, when would you ever use this? Well, I'm not really sure, probably could look it up, but I'm not really sure of a way where you would do it on numbers per se, but there is some magic that you can use, and I'll show you how this works. So let's go down to the end of our code here, and we have, let's say we have we are leasing apartments, okay, and that's the scenario that we're in, and we want to get some stats on the person that's moving in. So we have someone that wants to rent an apartment from us, and we need some vital information. So let's print to the screen here the values that we want to keep. So we'll put values, and we'll have single or married. So these are like either or, okay? With male or female, let's try that, and maybe minor or adult. Okay, not that a minor would necessarily be renting an apartment, but let's just play along here. And what we'll do is create a key. And if you think of these as either this value is 0 and this value is 1, and this is 0 and 1 and 0 and 1, we can create an index, like a key. And so single male minor, we'll just make that SMM, would equal 0, okay, because it's 0, 0, 0. So we're thinking of this in binary. And single male adult, okay, so 0, 0, 1 in binary could be represented with the 1, and we can go all the way through all of these, and then we get to married female adult, which would be the very last key. So if we just create one for every single combination, and we finally get to the end, we have married female adult, this would be 1, 1, 1, which if we go back to our binary counter here, it's 1, 1, 1, which is 4, 5, 6, 7. So we can represent this as 1, 1, 1. We can just represent it as 7. So we'll put married female adult equals 7. So the computer is, we're seeing it as the number 7, but the computer is going to, can do this in binary. It's going to see this as 1, 1, 1. It's going to see this as 0, 0, 1, and this as 0, 0. And that's how that's going to work. So to prove to you that this is actually valuable, let's take person 1. This is the person that wants to move into the apartment. And let's say that person is a single male adult. Okay, so SMA, which is what we've done here. So single male adult 0, 0, 1, which is equal to 1 in binary. So we do that, and we do the Bitwise XOR, which we just talked about. And sorry, this is going to be no, that's right. Okay, and then 0. Let's try it this way. Let's do 0 Bitwise XOR and then SMA. There we go. That'll work. So what we're doing is we're starting with a person that has the default single male minor. Okay, person is equal to 0. That's going to be the default for each new person. And we're going to do the Bitwise XOR with single male adult. And what we're hoping is that when we run this, the resulting value of this will be 0, 0, 1 to represent single male adult. So again, we've taken a brand new person and we've done the Bitwise XOR for single male adult, which is the binary representation of 0, 0, 1, which works with our key here. So if we go down and we do print, and we can format this in a way that gives us 3 places in binary. And person 1. Okay, so this string formatting is essentially telling us to format person 1 as a 3-bit binary string. And if we run this, we get 0, 0, 1. So in that case, we know that this person is a single male adult. And all we did was take a new person and make them a single male adult by using Bitwise XOR. Now if we change this to MFA, so that would now mean married female adult, and we run that, we get 111, which is married female adult. So you can start to see how this could be very powerful. So if you have a list of values that are either on or off or one or the other, so there's just 2 choices and you have lots of them, you can create this type of key. And you could create maybe like a list or a dictionary or something like that, some kind of object that can hold all of these in one. And you could create a function that could initialize a new person or loop over a group of people and assign the correct values to them, and they would be stored in binary or numerically, and you can just output them in binary and you write a function to spit out the corresponding values instead of the numbers. Whatever you want to do, it doesn't matter. So, but this is a practical application of using bitwise operators. So you're manipulating the bits in binary, but you're then going to use those bits to represent variables much greater than just the numerical representation of that. Okay, so I hope that helps, and that ends our video for today. So thanks for tuning in, and we'll see you at the next